Okay, let's move on to this next question here, which says a sociologist wishes to conduct a poll to estimate the percentage of Americans who favor affirmative action programs for women and minorities for admission to colleges and universities. What sample size, so this is a sample size question, what sample size should be obtained if she wishes the estimate to be within 4 percentage points with 90% confidence if? So we've got two cases here. So the first case is if she uses a 2003 estimate of 55%. So this is kind of like a prior estimate here. Prior estimate. Obtained from a Gallup Youth Survey. And then the second case, case number one, case number two, is she does not use any prior estimates. Okay? Now, the first thing you want to do kind of is just figure out if you're finding the sample size for estimating the percentage, which we are in this case, or the mean. And the question is fairly clear here. It says a sociologist wishes to conduct a poll to estimate the percentage of Americans. If it said something like to estimate the mean, then we would use a different kind of formula. So let me go over here and show you the two formulas that you want to focus on. So here in chapter 9, you've got sample size formulas, and this first bullet here is for estimating the population proportion, and this is the one we want to focus on. This bullet down here is to estimate the population mean with a margin of error at a 1 minus alpha times 100% confidence. So notice we have two different formulas here. One formula, this first formula here, says use this where p hat is a prior estimate. And then the second formula down here, this one here, says use when no prior estimate of p is available. So these are the two formulas that we're going to use. One when we have a prior estimate here, and the other when we have no prior estimate. So let's go ahead and just jot these formulas down. N equals p hat 1 minus p hat times z alpha divided by 2 divided by the margin of error squared. And then the second formula looks like this, 0.25 times z alpha by 2 divided by the margin of error squared. Now, this first question here, the first part, says we have a prior estimate of 55%. So that's p hat. The other thing we need to know based on the formula, and if you look at the formula closely, you'll notice we need to know p hat, we need to know the margin of error, and we need to know this z alpha by 2. So we've already got p hat. The margin of error says, and if we go back to the question, what sample size should be obtained if she wishes the estimate to be within 4 percentage points? So the margin of error is 0.04. And then the only other thing we have to know is this z alpha by 2, and we're going to get that number from our formulas and tables as well. So let's go back over to our formulas and tables. And we're going to scroll down to Table 5, which is right here. At the very bottom of Table 5, you'll see confidence interval critical value, Z alpha by 2. So all we want to do here is look at the level of confidence. So we want to be 90% confident. 90% is this first one here. Tells us the critical value, Z alpha by 2, is 1.645. So this number is 1.645. Now let's go ahead and plug everything in. 0.55, 1 minus 0.55 times, and here we're going to plug in the Z alpha by 2 in the numerator, 1.645 over the margin of error, 0.04. And we're going to square all of that information. Okay. Now, once we multiply all of this out, you're going to get something like 418.59. But we're always going to round this up to the next integer, even if this number here was a 4. So our sample size needs to be at least 419 individuals for us to estimate the true percentage within 4 percentage points with 90% confidence. Okay, now we'll move on to the second part. And this piece here, once you get all of these numbers up here, once you figure out what your p hat is going to be, of course, the second piece, we don't need any prior estimates. But once you figure out the margin of error and Z alpha by 2, you pretty much can just use these same numbers here. So let's go ahead and plug these numbers in. Z alpha by 2, 1.645, margin of error. And the only time these numbers are going to change, this Z alpha by 2 and the 0.04, the margin of error, is if the question specifically states that we're changing the level of confidence or we're changing the margin of error here. That's the only time that these two numbers here will change. Now don't forget the squared here. Now we're going to compute this value. We're going to get something like 422.82. And again, we're always going to round this up to the next integer. So 423. Okay, let's move on to the next question. And this looks like a hypothesis testing question. If you'll notice here, it says use the classical approach. So we know we're dealing with hypothesis testing. We just want to figure out if we're testing the mean or the proportion. So let's read through the question. A test of sobriety involves measuring of the subject's motor skills. The average score is said to be 35. A sample of 20 randomly selected sober subjects takes the test and produces a mean of 41 with a standard deviation of 3.7. So we're first going to give this test to the sober subjects, just to kind of measure what people should score on this test that are actually sober. And then that will help us better determine when we're dealing with someone who is intoxicated. And so if you read closely there, it says a sample of 20 randomly selected sober subjects takes the test and produces a mean of 41, a standard deviation of 3.7. So we know we're dealing with 20 individuals, and of course X bar, the sample of those 20 individuals, is 41, and the sample standard deviation is 3.7. At the 0.01 level of significance, test the claim that the mean for this test is greater than 35. So we're doing hypothesis testing here for the population mean. So let's go ahead and look at step 1, which is to state the null and alternative hypotheses. Test the claim the mean for this test is greater than, so the mean is greater than 35. And then, of course, the null mean is equal to 35. Step 2, state alpha 0.01. Step 3, we are going to compute the test statistic, which is x bar minus mu 0 s over the square root of n. So x bar, remember, is the sample mean. So go back into the question where it talks about a sample and then produces a mean of 41. So 41 and a standard deviation of 3.7. Mu 0 is our sort of standard. It's what we're comparing our sample to. And n, the sample size, is 20. So let's plug everything in. Over S, 3.7, square root of 20. So we get 7.25. And remember, this 7.25 means that our sample average is 7.25 standard deviations above what they said the average score was. Okay, so just kind of keep that in mind as we're going through. That's strong evidence to say that the average is actually greater than 35. Now, step 4. Is to find, since we're using the classical approach, to find the critical value. And the critical value here is what we call T alpha. And this region here is called the critical region. Now, to get the T alpha value, we're going to use the inverse T function. And inverse T, the argument here is just alpha and degrees of freedom. So alpha is 0.01 degrees of freedom, remember, is the sample size less 1. So 20 minus 1 gives you 19 degrees of freedom. And when we enter this into the calculator, you should get 2.54. And we know that the t-score is going to be positive because it's to the right of the mean. It's to the right of 0. Step 5 is to compare the test statistic with the critical value. We say something like this: if T0 is greater than positive T alpha, reject HO. And so we can see clearly that 7.25 is definitely greater than 2.54, and so therefore we reject the null hypothesis. Step 6, reject HO. So if we reject HO, then we're saying that the results are statistically significant and there is sufficient evidence to support the researcher's hypothesis. Okay, so let's move to the next page, next question. And again, another hypothesis testing question. According to the U.S. Census Bureau, in 2009, 2.1% of Americans worked at home. An economist believes that the percentage of Americans working at home has increased since then. Increased since when? Increased since 2009. What was it in 2009? It was 2.1%. Okay? That's the researcher's hypothesis. The researcher in this case is an economist. An economist believes that the percentage of Americans working at home has increased since then, right? Since 2009. So here's what he do to test his hypothesis. He randomly selects 150 working Americans and finds that 6 of them work at home. Question: do a higher proportion of Americans work at home? Okay, so we're definitely doing hypothesis testing for the population proportion, P. So step 1, determine the null and alternative hypotheses. So P has increased since 2009, which was 0.021. And P is equal 0.021. Okay. Step 2, state alpha. Step 3, compute the test statistic, which in this case is P hat minus P0, square root of P0, 1 minus P0 over N. So P hat is X over little n, the sample size, which is 6 over 150, 0.04. P0, the standard, is what it was in 2009, which was 0.021. And then N, the sample size, is 150. Okay, so let's plug everything in here. 0.04 minus 0.021 over the square root, 0.021, 1 minus 0.021 over 150. And so Z0, we get 1.62. And now we move on to step 4. And we're using the p-value approach. So for a right-tail test, if you look on your formulas and tables, you'll see that you've got Z0 here, and then you've got the region shaded in here, which is our p-value. So Z0 we just calculated, so we can write that down, 1.62. All right, and then the formula for the p-value is equal to the probability that Z0 is greater than, no 0 here, that Z is greater than Z0. So let's go ahead and plug in z greater than 1.62. Now remember, when we find the area to the right under the standard normal curve, we either have to use the complement rule, so 1 minus the probability that z is greater than 1, or we can use symmetry, and I kind of like to use symmetry, which says that the area to the right of 1.62 is the same as the area to the left of minus 1.62. And if you draw a picture out, you can see this very clearly, and we talked about this in class several times. So now all we have to do is just look up minus 1.62 from table 5, and we get the p-value, which is 0.526. Okay, so step 4. Now step 5 is to compare the p-value with alpha, and we say something like, if the p-value is less than alpha, then we reject the null hypothesis. And so the p-value is 0.0526. Alpha is 0.05, so the p-value is not less than alpha. Therefore, we fail to reject. And so that's what we'll say here in step 6. We fail to reject the null hypothesis. So here we're saying that there's not sufficient evidence to support H1. So essentially, we can say that there's not enough evidence to support the fact that the percentage of Americans that work from home is different today than it was in 2009. Okay, so next question here, page 17. Looks like a linear regression type of question. It says a study was conducted to investigate how people with a hearing impairment communicate with their conversational partners. Each of 13 hearing impaired subjects, all fitted with a cochlear implant, participated in a structured communication interaction with a familiar conversation partner, family member, and with an unfamiliar conversational partner, who also was instructed not to take the initiative to repair breakdowns in communication. And then we're kind of given what the data represent here. The total number of words used by the subject in each of the two conversations is given below. So essentially what happens here is we kind of have this person here that is impaired and then we have this person here have a conversation with someone that they are familiar with, and then also have the conversation with someone that they are unfamiliar with. And so X counts the number of words used by the subject in each of the two conversations. So the number of words that this guy uses with the familiar partner is X. And the number of words that the hearing impaired person uses with the unfamiliar person is what we call Y. Okay, so that's kind of the idea. That's kind of what's going on here with the question. Now, the first part of the question says find a linear plot the scatter plot. So what I've done here is I've just used Excel to kind of give us a good indication of whether or not the data, the paired data, is positively correlated or negatively correlated. So here's the plot of that. And it looks like to me that there is some sort of positive linear relation here between X and Y. And so the next question asks us to find the linear correlation coefficient R. Now, what we're going to do for R is we're going to look at the printout. Okay, I believe this is on the next page. So find the linear correlation coefficient R. Now, to get this value, what we're going to do is we're just going to look at the printout that I gave you. Okay, I think it's on the next page. Let's see. Here it is. Okay. So what we're going to do is we're going to look at the what we call multiple R. And so multiple R is the linear correlation coefficient R. Now again, to determine the sign of R, because what Excel will do is it will give you the absolute value of R, which will always be positive. So we have to look at the scatter plot to determine if R is going to be positive or negative. And in this case, it's positive because the scatter plot is positive. So let's go ahead and write that in. Okay. Now we'll find the regression line. And so remember, the formula for the regression line is y hat is equal to b1x plus b0. Remember, b1 is the slope and b0 is the y-coordinate of the y-intercept. So something like this. Okay, and again, we're going to get these from the printout. Okay, so let's go back over here and I'll show you how to get the slope and the y-intercept. So the slope is going to be here, and the y-coordinate for the y-intercept is going to be by intercept. So this is going to be b0. So let's go ahead and plug these values in. B1, which was 0.62, and I'm just going to round to 2 decimal places, plus B0, 20.13. And this is the model. This is the regression line here. Okay, now we're asked to predict the number of words used with an unfamiliar partner. Remember y, so predict y hat if the number of words for a familiar partner is 140. So remember, x represents familiar, so x is 140. So let's go ahead now, and again, we just use our model here. We just plug in 0.62 times x, which is 140, plus 20.13. So we get y hat is approximately 106.93. 106.93. We'll just round that. We'll say approximately, y hat is approximately equal to 107 words. Okay, and then the last part of the question says find the residual. So the residual is equal to the observed minus the predicted y. Observed y minus predicted. Okay, and another way to think about this is observed is what we get from the table. That's what the person that did the experiment, that's what they actually observed with their own two eyes, and then predicted is y hat. This is our model value. And y is the table value. So if you go back up and look, for x equals 140, y equals 101. And of course, y hat, we got 107, approximately 107. So this gives us a residual of minus 6. So the residual is minus 6. And that just means that this individual was actually below average in comparison to all the other individuals. Okay, next question. Okay, so this question, there'll be a question similar to this where I give you a frequency table that's dealing with qualitative types of variables and then just ask you to create a relative frequency distribution. So let's kind of see what the data represent. In a national survey conducted by the Centers for Disease Control to determine health risk behaviors among college students were asked, how often do you wear a seatbelt when driving in a car driven by someone else? And the frequencies are given below. So always is kind of the largest category here, and then never is the smallest category, which is what we would hope. Now, to get the relative frequency, all we really want to do is just add up 125 plus 324 plus 552 plus 1257, so on and so forth. And we get 4776. And then to get the relative frequency, what we're going to do is we're just going to take each frequency, so for the first one, 125, and divide by the total, 4776. And I'm going to round this to 2 decimal places, so we get 0.03 here. 324 divided by 4776 gives 0.07. And then 552 divided by 4776 gives 0.12. And next we get 0.26 and then 0.53. So that's the relative frequency. So we can say something like 53% of college students always, somewhere around 53% of college students always wear seatbelts when riding with someone else in the vehicle. And then the next part, part B, just asks us to make a histogram, a relative frequency bar graph from this, relative frequency bar graph, not a histogram. A histogram is for quantitative type of data. So let's go to the next page here, and what I've done, I've just kind of typed this into Excel, and so we've got never is 3%, rarely is 7% of college students, sometimes is 12%, most of the time is, and then always is the 53%. Okay?